Okay. All right, guys. So let's get started. Welcome back to this class. And so first, let me get started by looking at the things that we have covered in the last class. Okay. So just to give a quick recap, because that's an important class, because we discussed in more detail about signed number representation and in general representation of data. Data can be coming in the form of signed as well as unsigned. Unsigned, we don't have as much of a problem because we don't have to worry about the sign. On the other hand, when we talk about signed representation, that's something I need to be more careful about. Okay. All right. So just to give a quick recap. All right. So in the last class, we covered the concept of two's complement representation in more detail. Okay. Again, whenever you think about two's complement, you need to think about that as an operator that can negate a given number. Okay? Just like how, so your two's complement operation is essentially equivalent to the negative operation, the symbol negative sign. When you place the symbol in the front of a number, that basically negates that number in exactly the similar way. When you do the two's complement operation on a given number, you are negating that number. They are basically equivalent. There's no difference between them. Okay. The way we represent negative numbers in the devices, as in the binary formats, is using the two's complement representation, because there is no other way that we can represent it in the most practical sense, right? This is what we have seen in the last class. You know how to opt. So in the last class, we also looked at two different ways of computing the two's complement of a given number, right? This is what we've seen in the last class. One way is, of course, you take the ones complement of a given binary number. If you want to find the two's complement, take the ones complement. How do I get the ones complement of a binary number? It's as simple as flipping the bits. So you have let's say you have some given binary number. All I have to do is I would complement each individual bit. When I say complement, 1 becomes 0, 0 becomes 1. That's what I mean by complement. So I complement each individual bit, okay? And then I add 1 to that resulting number. I get the two's complement of that particular number, okay? So that's how I would compute two's complement. By computing one's complement, adding 1 to that, I get the two's complement. The other way of doing this is which is, I would say, my preferred way. Although you have to know how to get it by the ones complement approach, because we'll be using that later on in the course. The other way is, of course, you go from the right. For a given binary number, you go from right to the left, okay, and you do not change anything. You do not complement until you hit the first one including. So you do not complement the first one as well. Okay, and subsequent to that first one in that binary number, you complement all the bits, and that's how you would get the two's complement of a given number. Okay, so those are the two different ways that we have reviewed in the last class. Okay, and we took various examples. Okay, for example, if I want to convert a given number minus 72 into a two's complement represented binary format, how would I do this? Okay, again, the approach is you take the two's complement of 72 first. I'm sorry, you take the binary equivalent of 72 first. Okay, let's say I want to convert that into an 8-bit binary equivalent number. Okay, now I would convert 72, the positive 72, into the 8-bit binary number first, and then I would apply the two's complement over that binary number to make it to obtain the negative 72 representation. So two steps, right? So first, if I want to convert that into an 8-bit, two's complement signed number, I would do step 1. I would compute 72, I would express 72 as a 8-bit binary number. So whatever that number is, I get that. Okay. And then I want to make this negative, right? So that's positive. I want to make this negative. How do I do this? I take the 2's complement of this particular number, and I would get the negative equivalent of negative 72, or negative equivalent of 70, this particular number. Okay. All right, because taking the 2's complement of this number is basically making this negative, right? So that's how I would get it. So it's a two-step approach. If I want to express 72 as an 8-bit signed number, how do I do this? Then basically I just take the binary equivalent of that number, and I get then that's what it is, right? That's the final answer. Okay, and so these are some of the things that we have covered in the last class, and we also looked at an important concept about extension, right? Whenever I'm trying to do any computation between m and n are binary numbers, I need to make sure that they are of the same size. Okay, and the way we extend the numbers depends on if the numbers are signed or unsigned. For example, we have looked in the last class that, for example, let's say you are given some number 1100, and I specify that this number is a signed number. Then if I want to extend that to 8 bits, I need to make sure that after the extension, the sign of the number doesn't get changed, and the value of the number doesn't get changed, right? Obviously, by looking at this number, because I mentioned that this is a signed number, by looking at this number, I can tell that this is a negative sign, right? Because the most significant bit, even in the 2's complement approach, the most significant bit still represents the sign. Okay, is indicative of the sign. Okay, because if I take a number, because if I take some positive number, which is indicative of the most significant bit here, taking the 2's complement of this number would basically make it positive, make it negative, right? So 0 becomes 1 automatically. So the 2's complement of this number will be 0, 1, 0, 0, 1. So that's the positive version, that's the negative version of the same number. Okay. So that works. So in this case, if I want to extend that to 8 bits, I would basically pad 4 additional ones and 1, 1, 0, 0, right? So that will be how I would extending signed numbers. Okay, so that's a negative number. That's how I would extend that negative number. By adding these ones, I'm not really adding any additional value to it, because if I want to know what is this number represented in the form of negative in the conventional representation, how do I do this? I basically this is negative of a positive equivalent of this number. The positive equivalent of that number is obtained by taking the 2's complement of that, which is 0, 0, 1, 0, 0. All these additional ones that you added really become zeros, and it really does not add any value to it. So so these two numbers are equivalent, expressed in different ways. That's the 2's complement representation. That's your conventional representation. That's the only difference. Okay. If I were to mention explicitly that this number is an unsigned number, in that case, what would that become then? If this were an unsigned number, okay, if I want to extend that into 8 bits, how would I extend it? Again, I would basically, because there is no sign associated with this, I would extend it with basically zeros. So the way you extend numbers depends on if the number is signed or unsigned. That's very important to note. So in this case, if I specify this as an unsigned number, that's how I would extend the number. Okay. All right. Any questions on this? Okay, so this is something that we have covered in the last class. And now, okay, let me.
Fred,
Yes.
I just have a quick question.
Yeah, please.
You erased it, but you have two 4-bit binaries, right? That you did on the right side.
Uh-huh.
The second binary with 4 bits. Um, how come you kept the last 3 bits same? You know what I mean?
Can you give me the binary number?
When we extended so like when we extended to 0000,
Mm-hmm.
yeah, that one. That's what you used.
Okay.
So 000000,
Mm-hmm.
and then you use zero. Yeah, yeah.
Yes.
That's what you did.
Right.
But in order to change that, the second binary, did you? How come you kept the last three? No, no, no. I get the zeros, but before the last example, you gave another example. I forgot.
Okay. So that was 1111, right?
Yeah, yeah.
Okay. And
That one. Yeah.
yeah. So in this case, all I've done is extended that number because in the previous example we took this as an unsigned as a signed number.
Right.
So when I want to extend a signed number to 8 bits, okay, I need to make sure that I extend so that the extended number has the same value and the sign. Now, the most significant bit before extension was this, right? The most significant bit after extension is this, right? Now, so after extension, you can see the most significant, so both, so before extension, after extension, these are both negative numbers. I have not changed the sign. That's one important.
I did the. Oh, okay. I did the extended part.
Mhm.
Is this the only thing I don't get is when we the complementing
Oh,
this
okay.
complement like this. Yeah.
Oh, okay. Sorry. Let me. So what I was trying to say was I can also extend. I can represent this number as negative of the positive version of this number, right? And the negative of the positive version of this number would be 0, 0, 1, 0. Did I put 1 there before?
No.
0,
So this
0.
is where I'm confused.
Okay.
This is where I'm confused on the second binary on the
On
right,
this one. Okay.
where 01 on the where 0100.
Mm-hmm.
How come you kept last three same? Because wasn't it when we complement this version?
Oh, okay. Last three, I mean these ones same.
Yeah, yeah.
Okay.
That's what I don't get.
So the two's complement, the way I do the two's complement is I did the quick way. One way is, of course, you complement everything. Okay. If I do or take the ones complement of this, which is 0, 0, 0, 0, 0, 0, 1, 1, right? And then that's the ones complement. If I want to take the two's complement, I need to add 1 to that.
Oh, okay. You jumped. Okay. Yeah,
Right? So that becomes 0, 1, 0, 0, 0, 0, 0, right? Here I took the second approach. I do not change anything going from right to left until I hit the first one. First one included. I do not change anything until I hit the first one. This is the first one going from right to left. And then I complement all the bits. Complement all the bits. Does that make sense now?
that makes that does. Thank you. Yeah.
Okay, great. All right. So now let's move forward and then quickly spend a little bit time on the subtractions using the complements. Okay. And the idea is pretty, now that you know what the two's complement actually does, the idea is actually pretty intuitive now, right? Just like how we mentioned last time, if I want to do m minus n operation, I can write this as m, as if I'm adding m to the negative n. right? It's basically exactly the same thing. I'm writing it a different way. That's all. Okay. Now, because negative m, I can also get negative n as, I can express negative n as, for binary, I can express this as 2's complement of n. That's the same thing. Exactly the same thing. Okay. Now, so what kind of answers would you get? How do I know that when I do this operation, I'm going to get the right result? What happens when m is larger than n? I have two possibilities here, right? I have either m larger than n or m less than n. So let's actually look at two different possibilities and see if, and I want to generalize this so that so I'm proving it for any case, okay? I want to make sure that this technique of 2's complement subtraction works all the time. So I want to generalize m and n. So what I will do is, let's say, and again, I want to mention that this complement subtraction that I just mentioned, it's not just specific to binary operations, okay? You can do this for any number system, but for now, I'll just confine myself to binary operations, although this can be applicable to any number systems. It's more relevant to binary. Let me put it that way. So let's say I am taking m and n. M and n are both n bit numbers. If they're not of the same size, you know how to make them the same size, right? Through bit extension. So let's say m and n are of the same size. Let's say my m is given by a n minus 1, a n minus 2, a 0. My n, again, that's an n bit number. My n is given as bn minus 1, bn minus 2, b0. So those are two n bit numbers, binary numbers. Okay. Now I want to find m minus n. How do I do this? I take m, add to that the 2's complement of n, right? Because the same thing, m minus n would be m plus minus n. 2's complement of n will be minus n, right? All right, so let me put that thing down in the form of an expression now. So my m is a n minus 1, a n minus 2, a 0 plus, what is the 2's complement of n? How do I find that? 2's complement of n is again 2 power n minus n, right? So 2 power n will be, again, this is very critical. I hope you get this. I hope you remember this. If I have 2 power n, how do I express this as a binary number? 2 power n is not binary. I want to express this as a binary number. What would that be? I hope you still remember that. 1 followed with the n zeros. That's perfect. 1 followed by n zeros. So basically, I add 1 followed by n zeros. So these are n zeros minus n, which is, which is the uppercase n, which is bn minus 1, bn minus 2, so on, b0. All right. Are you with me until this point? Subtraction, adding the complements would work in any base. It's not just specific to binary. You can do the complement approach in decimal, octal, hexadecimal, doesn't matter. It will always work. Okay. All right. So now I'm going to rearrange the terms. So again, this is basically a minus n. I have two cases here. Two cases, right? Consider case 1, where my m is larger than n. If my m is larger than n, what do you expect? My m minus, what can you say about m minus n? M minus n will be positive, right? It's a positive answer. M minus n is larger than 0. Okay. So now what I'm going to do is, I would basically rearrange these terms a little bit. So what I'm going to do is I'll take this r power n in the beginning, to the front, okay, plus, and then you have a n minus 1, a n minus 2, a 0, minus b n minus 1, b n minus 2, b 0. Now what can you say about this result? Let's say I call this c n minus 1, some answer c n minus 2, so on, c 0. Now this particular result, n digits long, is a positive answer. It's positive, right? Because I assumed in this case that n minus n is larger than 0. So in other words, what I get is 1 followed by n zeros plus this quantity, whatever that is. That's n digits long, n bits long. Or in other words, I would be adding cn minus 1, so on, c0. So I have n zeros here. That's an n bit long number. The result will be 1, cn minus 1, cn minus 2, because for each bit I'm basically adding 0, the same number comes out. Now what is my answer then? What is the answer that I want in this case? I want basically m minus n. M minus n, or in other words, this number minus this number, which is this number. I'm getting an additional 1 here. Do you see that? I'm getting an additional 1. Do I need that additional 1? I don't, right? I don't need this additional 1. I can cancel out. Because I'm interested, as far as I'm concerned, or this operation is concerned, I'm basically interested in this answer. I'm getting this additional 1. I would just cancel that. All right, let me take a pause. Let me see if you understood what I just did. Does that make sense? We are interested in m minus n result. Or in other words, this is my m minus n. I call this cn minus 1, whatever that result is, cn minus 2, c0, which is a positive result here because I assumed m to be larger than n. So as far as the operation is concerned, this is the answer I would like to get. Now when I'm doing the 2's complement subtraction approach, I also get an additional thing, or at the end carry, we call that the end carry, this one, additional 1, which is not really, which I really don't need because that's the answer. So I just discard that end carry. So that's end carry. Discard it. Okay. Take an example that will make more sense. Let's say my m is 0, 1, 0, 1, n is okay, let me check. N is 0, 1, 0, 1. Okay. Now m is larger than n. In other words, that's plus 7. That's plus 5. I want to find m minus n. So you take m, which is 0, 1, 1, 1. You add to that the 2's complement of n, which is, again, going from right. That's the 1, doesn't get changed. Everything else changes, complements. That's 1, 0, 1. Okay. And what do I get? The answer is, of course, 2. That's what I expect. So that's 1 plus 1 is 0, 1. 1 plus 1 plus 1 is 1, 1. So that's 1 and 1 here. 1 plus 1 is 0, or 1, 0. 1 goes here. 1 plus 1 is 1, 0. See the end carry. This is the end carry. The end carry. This is the end carry. The same end carry here. That's the same end carry. I don't need it because my answer is this. That's my answer in 4 bits. So you discard that and you get the answer. So you'll always have an end carry. When my m minus n operation is positive or larger than 0, you'll always end up with an end carry. You discard the carry. Whatever answer you get in n bits, that's your answer. So it works all the time for m larger than n. What happens when m is less than n? Are you with me until this point? For the first case, any questions on the first case? Okay, very good. Now let's get to the next case where m is less than n. Exactly the same thing. I would do exactly the same thing. Okay. Case 2, m is less than n. If I want to do m minus n, can I write this, because m is, so in this case n is larger than m, can I write this as some negative of a positive answer, right? Because if m is less than n minus m is larger than 0. If m is less than n larger number minus the smaller number is going to be larger than 0, right? So, like for example, if m is 5, n is 7, m minus n would be minus of 7 minus 5, which is minus 2. You can write it that way. So this is the answer. This should be the answer, right? Now again, this is a negative of some number. So I can also express this as the 2's complement of n minus m, right? Every time you see the negative sign on the front of a number, you can also express that number as the 2's complement of that number, of the number in the bracket, or of the positive number. Okay, so I hope you get that. Now let's do the same thing now with the 2's complement approach. Now m again is an minus 1, so on a0, that's an n-bit number. N is bn minus 1, so on b0, another n-bit number. So m minus n, exactly the same thing. So I do m plus the 2's complement of n. So I take an minus 1, so on a0, plus 1 followed by n zeros, plus or minus, because that's the 2's complement, right? So 1 followed by n zeros minus n, which is b, n minus 1, bn minus 2, so on b0. Same thing. Taking m, adding to that the 2's complement of n, which is this one. The 2's complement of n is 1 followed by n zeros minus n gives me the 2's complement of n. Okay. All right. So what I'm going to do now is, because my b is larger than n, or my n is larger than m, I would basically put this as 1. I would rearrange the terms again. So that's 1 followed by n zeros minus bn minus 1, bn minus 2, b0 minus an minus 1, an minus 2, a0. All I've done is just rearrange the terms a bit. So that's basically saying this is minus n minus m. Now this, whatever this quantity is within the brackets, that's a positive quantity, right? Because that is n minus m. N minus m is a positive quantity. Okay, so I have basically r to the n minus this quantity. What do you, okay, then let me say that this, whatever that quantity is basically, well, you'll be able to see it. Let me just write it here. I'm just going to express this as 1, 0, 0, 0, 0, 0, minus, let's say if I compute this, let's say that gives me c n minus 1, c n minus 2, so on, c0. And what can you say about this number? That is 2 to the n minus, that's minus some quantity, right? Some n-bit number. Now, what can you say about this result? Do you see anything there? When I'm doing this computation, I'm expected to get minus of n minus m, or I'm expected to get the 2's complement of n minus m. What is the 2's complement of n minus m? That will be 2 to the n minus n minus m. Am I getting that? I'm getting that, right? That's 2 to the n minus n minus m. In other words, when my m is less than n, the answer is automatically the 2's complement, automatically expressed in the right format. I hope that I hope you're able to see that. Do you see that here?
It's n minus m plus 1, that's the 2's complement, right?
Can you repeat that? I'm sorry.
N minus m plus 1, that's the 2's complement, right?
N minus m. N minus m. No, it's the 2's complement is 2 power n minus n minus m. If I want to find the...
Oh, I see.
Yeah.
Okay, my bad, I'm sorry.
See, this is some value of, if I want to express this as in the 2's complement approach, I would take the 2's complement of n minus m, right? Which is 2 to the n minus n minus m. And when I doing the operation, subtraction operation as the 2's complement with the 2's complement approach, that's m plus 2 power m plus the 2's complement of n, which is basically that. I rearrange the terms, so that is nothing but 2 to the n minus n minus m. In other words, I'm expressing in my answer the n minus of n minus m automatically in its 2's complement equivalence. Just to give you an example here, again, let's take the same example here. This time, let me call this n, let me call this m. Okay, so I want to do m minus n. So I hope you're, yeah, let me do it this way. M minus n. Okay, so I take m, which is 0, 1, 0, 1. Add to that the 2's complement of n, which is 1, 0, 0, 1. Now, what is the answer I expect to get? Again, this is plus 7. This is plus 5. M minus n, I'm expecting to get negative 2. Right? And what do I get here? So 1 plus 1 is 0. 1, 0. So that goes there. That's 1. That's 1. That's 1. I'm getting an answer 1, 1, 1, 0. Is that the correct answer? Does that make sense? Is this whatever I'm getting here, is that the right answer?
I think it's not.
It's not? Okay. Why do you think it's not?
Because it's shows as a negative number.
It's a negative number. Yeah, it's showing as a negative. And shouldn't we be expecting a negative number? We should be expecting a negative number.
Yeah, actually, yes. Okay, my bad.
Right? No, so that's good. You brought it up because it's important. So that is a negative number. That's a good sign that it's a negative number because I expect a negative number because I'm trying to subtract n minus n. In this case, m is less than n. So obviously, I should get negative 2. The first indication, again, that's that's m plus the 2's complement of n. At the first indication, this is a negative answer because the most significant bit is 1. But what is that answer? If I want to express that in the conventional format with a negative symbol, how would I do this? I want to express this answer in this format, negative of some value, negative of some positive value, right?
2's complement.
2's complement. Yeah. So I take the 2's complement of this, which is 0, 1, 0, 0. And what is the, and which is?
And plus 1. Oh, when, no, my bad, yeah.
Negative 2. So again, very important. You should not be getting confused between the two approaches. Okay, very important that you keep track of that.
Okay.
Yeah. So that's negative 2. So that's good. That works. Does it make sense? So the answer is automatically in the right format. The negative, if it's a negative answer, the negative answer is right in the correct format. As long as I do not have an overflow that we considered in the last class, this operation works under all circumstances. Any questions on that? So in the first case, if m is larger than n, then we will have an end carry that you basically discard. In the second case, when m is less than n, you'll get a negative answer in the right format. If I want to express that in the right in the conventional format, then you take the 2's complement of that, and you will get, and then you can express it in the conventional format with a negative sign. All right, so that concludes our discussion on the 2's complement approach. It's very important because we'll be using that later on in the class. Now, there's an interesting thing about the 2's complement. You may ask me this question, right? Why do we need to go for the 2's complement approach in the first place? Can anybody think about a potential advantage of using the 2's complement approach, especially when in the context of designing systems, designing devices that can compute? What do you see the advantage as? Or do you see any advantage at all? Because if I were to do this on paper, it seems like it's not a direct approach to subtraction. You take m, and then you have to take the 2's complement of another number. You have to add them together instead of directly subtracting them together on the paper. Do you see any advantage doing this in the context of designing hardware?
If you use a 1 and a bigger than me, just guessing, maybe a reverse calculation?
A reversed calculation. Can
Which
you?
is kind of considered as like a negative, not like positive.
Okay. So I think you're getting there. You're getting there. Anybody wants to elaborate? I No, you can design a computer logic that can do subtraction. You can design hardware that can perform subtraction. But the advantage, as you may have noticed, is I can use, if I can design something, a device that can perform addition operation. Okay. Now, by using the 2's complement subtraction approach, I can use the same hardware because we are, as you can see here, we are doing the subtraction operation as an addition operation. You see that? By using the 2's complement approach, you're using the addition operation for subtraction operation application. So if I design a hardware for addition, I don't have to design another hardware for subtraction. I can use the same hardware for both addition and subtraction. So that makes it more efficient, right? That makes it more. That would make it or that would increase the functionality of my hardware. And when I'm trying to design hardware, I would like to do that. I would like to make my hardware more efficient, more compact. That way I can make it more compact. Right? Does that make sense? Okay. All right. So now, with that, let's conclude this number system discussions, and let's actually, delve into the more interesting aspects of designing hardware. Okay. Now, but as we are doing that, uh, I would like you to basically think about this process, right? It's very interesting if you think about it. You have these handheld computing devices that are so functional, that are so powerful, that can compute, that can be programmed, that can be used for multiple different applications, right? The applications are endless. And how are we able to do that in the first place? Again, at the end of the day, what you're really holding in your hand, your smartphone, is basically, it's not like a living thing. It's made of basically matter, and somehow man realized or figured out how to make it think. Of course, it's not, right now, the way things are, most of the time you're still, telling it what to do as programmers. But even then, it's able to compute very complex stuff. Okay. How is it being able to do that? Now, a computing device is very different from other electrical devices, right? Appliances, for example, a light bulb. You know how it works. You can think. You pass current through the coil in the light bulb, for example. The coil heats up and emits light, and that's how you use it as a light bulb. So that's kind of that makes sense, intuitive sense. Uh, a radio, for example, a radio, how it works. You have these antennas that can receive electromagnetic radiations. You can tune the frequencies by using the capacitor and resistor combinations and inductor combinations, and and that's how you can extract the waves and then listen to the radio. That makes sense. But what about a device that can actually compute? How is it happening, right? So, because at the end of the day, all the device can understand, right, is just voltages, currents, voltages, right, and that's it. So how am I able to utilize this for computations, right? So that's something I would like you to uh, think about and appreciate. What kind of clever designs the engineers over the time have come up with to make it possible, make these computations possible in the first place. Okay. All right. Now, so let's look at the introduction to logic. And through this, we would like to slowly, one step at a time, get to understanding how things can actually be made that can compute, how computational things work in the first place, how the hardware works in the first place. All right. So now, if you think about the computer, again, a computer is or any other computing device, for example, it's a very hierarchically built structure. Okay, just like how human beings or how animals are hierarchical structures. When I say hierarchical, that means we are built at different levels, right? We have a hierarchy. For example, let's take the example of myself. I'm a human being. And I am associated with a name. And this entire structure basically gives me that form, a one form, right? But it's a collection of different parts. I have hands, brain, lungs, heart, and so on and so forth, right? So it's a collection of all these parts coming together to form one. Yes, and if I want to go one hierarchy down, then your heart, the individual organs themselves, are made up of tissues, okay? A collection of cells, different tissues, different collection of cells coming together to form those organs, right? If I want to go down further, then each of these tissues is made up of these cells, right? And if I go down further hierarchy, then each cell itself is made up of molecules coming together. Okay. So it's a very well organized structure. Okay? So you have these cells coming together to form these tissues coming together to form these organs, the organs coming together to form the entire body. And this entire body is viewed as one single entity that works as one single entity. Exactly the same way, your computing device itself is a very hierarchically built structure. Okay, so if I want to break down the hierarchy, you start with the computing device or computing device. What you will see is your computing device is not a single entity. It's not like a single monolithic structure. It consists of multiple parts, multiple systems coming together to form that computing device that acts as one. Okay, you have system one, system two. They're all arranged in the appropriate manner so that you have communication between these different systems at all times. So if I go down further hierarchy, your subsystems themselves consist of multiple subsystems. Yeah, multiple subsystems forming that system. Okay. So when you're trying to build one computing device, it's not a matter of it's a matter of making these subsystems and making the systems, putting this system together to make the computing device. If I want to go down further hierarchy, the systems themselves are made up of multiple modules. Short modules, or the subsystems, are made up of these short modules that come together to make this subsystem. So modules are a collection of, again, if I want to go down further hierarchy, these modules themselves are a collection of simple logical building blocks. These modules are made up of logic building blocks. So I would like to take the analogy of of the Legos here. So the logic building blocks are similar to your Lego pieces. You have to put together the logical building blocks or the Lego pieces properly together to form a functional structure, right? So it's a bottom-up structure. It's not completely a bottom-up structure. You build with these Lego pieces, building blocks, to form these modules. Once you're at the modular level, once you have built these modules together, then you forget about the Lego pieces. Now you're working in terms of modules. Using the modules, you build the systems, subsystems, systems, and the computing device. So that's the approach that the scientists, or that's the approach that the engineers take to build systems, to build complex systems. So not everything is built at the molecular level. Not everything is built at this individual circuit level. Okay. So in this class, I would like to emphasize on the modular approaches to design. Okay. As engineers, again, the concept of modular design is not just relevant to this class. It's basically it's a universal technique, a universal approach towards building complex systems at the modular level. You don't want to be starting at the logical building blocks and building your computer at this level without the intermediate steps. So you have to go at the hierarchical level. Okay. All right. So logical building blocks, and then if I want to go further hierarchy, then these are made up of your individual circuits: transistors, resistors, capacitors, and so on. Okay. Your individual electronic components. Okay. Now, in this class, we're not going to spend too much time on the transistor level. Okay. We'll be focusing more on the logical building blocks, which is more fun, I would say, because you're working with logic. All right. So, and then and in this class, we're going to examine how we can actually put these logical building blocks together correctly so that you can get a functional system out of it. So that's the idea. All right. Now, so why are they called logical building blocks in the first place? So let's start with that. So we're talking about logical building blocks. So now let's talk again. That brings us to the idea of logic, right? So what do I mean by logic, or what do you understand by logic? Again, logic is not a new word I'm introducing in this class. That is something that you use all the time. You know, you're exposed to this. What do you think about what does that mean? What is logic?
I usually think of like a if-then statement, but in a simpler fashion.
Okay, if then, absolutely, that's kind of perfectly, you know, captures the essence of logic. That's good. Any other take on what do you mean by logic? True or false? Okay. True or false? With some constraints, right? A set of rules, something follows. Yeah. So everything is related in a way. So true or false, a set of rules, something follows, and or if then, they're all related. So what you're trying to say is that you have a conclusion to be made, and then that conclusion follows a set of rules. Okay, and the set of rules assumes some premise, right? So you have set of rules. The set of rules helps you reach a conclusion, some conclusion. Conclusion can be true or false in the simplest terms, simplest sense. Okay. And to get to that conclusion, of course, so what is the set of rules acting on? The set of rules are acting on some premise, some inputs. So we can relate all of these responses into this kind of an explanation for logic, or kind of idea about logic, right? So you have a set of rules, something is working on a set of rules. The set of, again, our ultimate goal is to reach a conclusion, right? A logical conclusion. And the set of rules, and of course, the set of rules is acting on the premise, some kind of inputs to reach that conclusion. It can be true or false. Just for example, you made a logical decision to come to the class today. Okay. So what is the premise here? You have, it's a Thursday, and it's 12:30 p.m. All right, and you know that you made a logical decision that when you have Thursday 12:30 p.m. Then that's your yearly 250 class. And a simple logic, and it's a very simple logical decision that you made, but it's still a logical decision that you have made. Okay, and you made a logical decision to come to the class. Of course, there's another possibility, which is Tuesday. We have the class also on Tuesday, same time. So your brain, if it's a Tuesday, and if your brain is presented by this data, then your brain follows the rules, makes the logical decision to come to the class as well. Okay. So that's the idea. So you can have logic at the very fundamental level. Okay, and of course your brain just does not take such simple logical decisions. Your brain takes much more complex logical decisions, right? But the interesting thing about computer logic is that you can actually build complex logic. You can make this computer take complex decisions, and you can build hardware for that, starting with these simple logical uh, uh, building blocks that can take simple logical decisions. So that's the idea about this hierarchical design, right? About this Lego analogy. So you have the Lego pieces, um, and you use these Lego pieces to build more complex structures. And we need to formulate some rules by which you can put the Lego pieces in the most effective or most efficient manner to form the most efficient structure. So this course is all about what are those rules. Okay. All right. So that's good. Now, when we are trying to design a computer, or a computing device, as an engineer, what are the things I need to keep in mind? Because again, as I mentioned before, we'll be starting at the basic building blocks, the logical building blocks, to start designing our modules. Okay, what do we want out of my device? Let's say you're the engineers working on building a computing device, building the hardware for a computing device. What are the things that you would, you know, that you would like in this? What are the things that you need to take care of while you're designing it? Any ideas from the class? You're building this device. What are the characteristics that you would like in your device? Simple. Okay. Keeping it simple. Can you elaborate? What do you mean? What do you mean by simple? As in simple to design it or simple to use it? Efficiency. Okay. Now again, efficiency can come in multiple different forms, right? Efficiency in terms of are you referring to power efficiency, or are you referring to computational efficiency, right? Okay, processing speed. You want this to be processing. Yeah, that's an important consideration. You want this to be processing at a large speed or high speed. Okay. What else? You had efficiency too, right? So let me call this because processing speed. We've already mentioned processing speed, so let me call that power efficiency. You want this to be power efficient. You don't want too much power being taken out by this device. Processing speed, efficiency. What else? Not overheat. Okay, not overheat. Now, why does it heat in the first place? Why does it generate heat? Why does it get hot? It gets hot when it's processing in some information, right? Of course, you need the other reason is, of course, you need to have pretty good heat dissipation arrangement there, so that all the generated heat is dissipated well. The other reason is, if it's taking a lot of power, and some of the power is basically being converted to heat, right? So if I can reduce the power consumed, then that also affects the heat generation. Anything else? An input and output capabilities, peripherals. Yeah. Yes. Simple interface. So the more simple interface you make, okay, the more complex as a designer, you need to make it more on the back end. It will be more complex, right? Because it has to be smart. It has to figure out what the user wants to do, and so on, right? So usually, for example, your iPhone, it's very simple to operate. Even you give it to a child, like a 2-year-old child, he'll figure out how to use it, just by using this finger swipes. But what goes behind the screen is much more complex, right? Now, with every swipe, the computing device has to figure out exactly what the kid is trying to do, right? So the complexity at the back end increases, but of course we want to make it simple for the users. From the user point of view, of course, we want to make it simple. What else? I'm surprised you did not come up with compact. You wanted it to be compact, want it to be small, handheld, if you and the more compact, the better, right? You want the computational efficiency in a very small, taking much smaller space. So yes, so that's good. That's a good list of things. And throughout this class, when we try to design this hardware, we'll keep these things in mind. We want to make this simple in terms of complexity, circuit complexity, the number of components that you would go into designing this. Now, because we are dealing with circuits, okay, now these, as we will see, these logical building blocks, the building blocks that we'll be using to make these modules, these are all electric circuits. These are all what is called the active circuits, electrically or active electric circuits. What it means is for these logical devices to work, I need to supply power to this. Okay, I need to apply a voltage for these logical devices to work. Okay, so what that means is if I have a lot of these devices, that means I should be applying a lot more power, right? So this power consumption increases as the number of devices increases in your design. So we want to make this, so we would like to see if we can actually obtain hardware with fewer number of components. Simple. We want to make this simple. And of course, at the same time, we want to make the computational speed higher with fewer number of components. When you use fewer number of components, again, the power efficiency increases, right? Because I'm not having components taking, fewer number of components. That means, less power consumed. Less power consumed, that means I'm not overheating it. Okay. Less number of building blocks or circuits, that means my design is compact. So it affects all of these aspects that you, as an engineer, you want in your device. Okay. All right. So with that, let's look at some of the simple building blocks that we'll be using to build our circuits that can perform all these complex operations. Okay. Now, over the time, as I mentioned during the first class, one of you asked a question about the textbook, right? Over the time, these logical building blocks and the rules haven't changed. So that's why, any book can be a good reference book for this. Any version of the book would be fine for this class because we are dealing at the very fundamental level. All right. Now, logic itself can be of two types. We have the combinational logic. And you have what is called the sequential logic. So for the first half of the class or the course, we'll focus on combinational logic. And then we'll examine what you mean by sequential logic. Now, again, it's not like sequential logic is completely different than what we have studied for combinational logic. Everything builds on top of each other. Okay. So if I want to understand sequential logic, I have to go understand combinational logic first. Okay. The fundamental building blocks that make combinational logic or sequential logic are exactly the same. All right. Now let's look at combinational logic. Well, what do I mean by combinational logic? What it means is if I have a system, if I design a system consisting of some inputs going into the system, some outputs, the combinational logic building or this module would be defined so that my outputs of this building block or my output of this device depends only on the present inputs. So these are all the present inputs. It does not depend on the history of the inputs. That's what I mean by that. When I say present, that means at this instance, what are the inputs happening at the inputs, at the input of this device? The outputs are dependent on what you apply at that present instance. Just like, for example, the state of a simple light bulb that depends on the switch position, right? You turn on the switch, the light bulb glows. You turn off the switch, the light bulb is turned off. It does not depend on if the switch was open or closed yesterday. It just depends on the present condition of the switch, present state of the switch, right? So that's combinational logic. Sequential logic depends, again, similar thing. Sequential logic depends, the outputs depend on the present inputs as well as the previous inputs or the history of the inputs. Okay. Example of a sequential logical circuit would be, your traffic light controller, for example. The sequence of lights that are happening, sequence of light depends on the previous outputs, previous inputs to the controller, right? So it has to follow through a particular sequence. So the output depends on the history. All right. Now, so with that, let's again, just to recap, because all my devices, it basically understands zeros and ones. It understands voltages. And for our class, when I say logical 0, again, corresponds to 0 volts. A logical 1 corresponds to a node voltage of 5 volts. Okay. So we'll not be talking in terms of volts anymore. We'll be talking in terms of zeros and ones. 0 corresponds to 0 volts. 1 level corresponds to 5 volts. Okay. Also, again, this is the way we speak. 0 level also corresponds to what is called false, the absence of false. The logical level 1 corresponds to true. Something is true, that means the node voltage at that point is 1 or 5 volts. Okay, just the convention. So just keep that in mind. Keep track of that. All right. Let's see. Okay. So now let's look at some of the building blocks. So let's start with what is called an AND gate. AND gate. Again, this is a logical gate, logical building block. So I'm talking about very fundamental logical building blocks that can perform by themselves very simple logical operations. Okay. So an AND gate, the symbolic representation for an AND gate would be that. Okay. Let's say your A and B are the inputs to this gate. F is the output for that gate. So that's an AND gate. Okay. Now, when we're talking about this logic gates, I can express the logical operation that this logical gate does as an algebraic expression. Okay. So if I want to express this as an algebraic expression, let me actually put this. So when I see something like this, the output F is basically expressed as A. As a statement, it is expressed as A and B. A and B. Again, remember that A can take 0 or 1 values, B can take 0 or 1 values. So all my nodes can only take values of 0 or 1. That's something that we need to keep track of. So we are working in binary. These are all binary. These values can be only 0 or 1. Okay. So F is A and B. As an algebraic expression, I can express this as A and dot B. This dot symbol is very similar to your product symbol in the algebra, in your regular algebra. Okay. So that's A and B. So when you see A, B, or even I can actually write this as simply AB, just like you would write in algebra, right? You're familiar with AB. So that's basically A and B. I will read it in this context as A and B. In fact, we will express logical expressions, logical operations as algebraic expressions, because you will see Logical operations are expressed as algebraic expressions, and we call this the Boolean algebra. Boolean. Now the difference between this, you will see that the identities are very similar to what you already know, with what you already know about the regular algebra. It's called Boolean algebra because, again, my variables, these are my variables of the algebraic expression, can take only 0 or 1 value. Unlike your regular algebra, where variables can take any value, right? But here it's only 0 or 1 value. You only have two values, two possibilities for each variable, 0 or 1. Okay, so we are now, when we talk about using these variables, expressing these logical operations as algebraic expressions, that corresponds to Boolean algebra. All right, so that's A and B. I can also express this operation in the form of a truth table that gives a snapshot of the operation of this device, of this building block. Okay. All right. A truth table. When I say truth table, what I'm trying to do here is I'm looking at all possible combinations between the inputs A and B, and the result of these combinations on the output F. So again, this is a logical building block, right? The conclusion is based on following a set of rules and a set of premises. So A and B are your inputs to that building block. It follows a set of rules. This is the set of rules it will follow. So these are all possible combinations between A and B, because A can take 0 or 1, B can take 0 or 1. So these are all possible combinations between them. I have 4 different combinations, right? And the rule that this particular AND gate would follow is, my F is true or F is 1, because 1 corresponds to the true condition. F is true if both A and B are true, right? So F is true only when A and B are both true. So for everything else, that's false. So basically I can write this as a statement: F is true if A and B are both true. So F is true if both A and B are both true. Okay, so that's your AND gate. All right, and your AND gate is an active electrical component. It is made, if I look inside an AND gate, that will be basically made up of transistors, resistors, capacitors, and so on. Your component, your regular components. Okay. So if I want to see what an AND gate would look like, if I want to construct one using at the circuit level, then it would be something like this. This is one way of realizing an AND gate. Okay. That's your resistor. You have 2 transistors. That's your, let's say, 5 volts. Let me call this A, call this B. Okay. And that's my output F. So this is how I would construct an AND gate. Now, let me see how many of you know how a transistor works. Just let's say, just raise your hand. How many of you, well, let me put it this way. How many of you do not know how a transistor works? Do not know how a transistor works. Okay, so let me explain it very carefully. In simple terms, as I mentioned in one of the class, a transistor is nothing but a three terminal device. It's a switch. Okay, it's a switch. It's like a switch. So this is called the gate of the transistor. Okay, let's say this is the source and the drain. Now it's a switch that is controlled by this, what you apply on the gate voltage, on this gate. Okay, so I can make this, if I apply, let's say, if I apply 5 volts on the gate, let's say, then my source is connected to the drain, so through a conducting channel. That means it's a conducting channel now. So my source is connected to the drain when the gate voltage is applied. On the other hand, if I take out the gate voltage, if I apply 0 here, then the conducting channel is lost, okay, and the source is disconnected from the drain. So that's an open circuit. It's like a switch. It's just that the closing or opening of the switch is controlled by this gate. At the very fundamental level, that's all you need to know, or you need to understand how a transistor works. Okay. It's a gate controlled switch. You apply 0 volts, the gate is open. Apply 1 volt, or 5 volts, or 1, logical level 1, gate is closed. In other words, the switch is closed, and I apply a 1, and my source is connected to drain. It's a simple switch. Right. So now, what I would like you to do is analyze this. If I apply different voltages here, A and B, like 0, 0, what happens when I apply 0, 0? What is the node voltage I measure here, or logical level I measure here? If I apply 0, 1, what would I be measuring, and so on. All the different conditions, right, for A and B, and see if this, what you get at here, corresponds to what you would, this particular table. Does it actually indeed function as an AND gate? Okay. So let's see that, and in the next class we'll continue this discussion. We'll look at all the different possible gates and start working on actually, formulating rules to put these gates together to form more complex logic. All right, so with that, let's end this class, and let me see if you have any questions.